Everything you see is built from just 17 particles. Scientists wrote them into one book, the Standard Model, and for 50 years it has passed every test we throw at it. It is the most accurate theory humans have ever made, and it is broken. It cannot explain gravity, the force holding you to your chair right now. It has no room for the invisible matter that outweighs every star. It says a tiny particle should weigh nothing, yet that particle clearly has weight. Tonight we hunt the cracks, a muon that spins off the rules, a neutron that cannot decide when to die, a mirror between matter and antimatter that should have left us with nothing at all. If a universe that ignores its own rulebook pulls you in, like and subscribe and stay close. Prepare yourselves, we begin. Look at your hand. Every atom in it, every atom in your chair, in the sun, in the farthest galaxy, comes from one tiny box of building blocks. Just 17 kinds of particle. That is the whole set. Physicists gathered them into a single theory and gave it a plain name, the Standard Model. Think of it as the universe's rulebook. It lists every basic piece of matter and every force that shoves those pieces around, and it tells you exactly how they behave. Here is the wild part. This rulebook works almost perfectly. For 50 years, scientists have hit it with every test they could dream up. They smashed particles together at nearly the speed of light. They measured tiny numbers out to more decimal places than the width of a hair compared with the distance across a whole city. Every single time the book got the answer right. In one famous case, it predicted a particle, the Higgs boson, decades before anyone found it. Then, in 2012, a machine the size of a small town dug it up, sitting exactly where the math said it would be. No theory humans have ever written has been this accurate. If science handed out trophies, the Standard Model would fill the whole case by itself. And yet the people who know it best will tell you something strange. The book is incomplete. Whole chapters are simply missing. There are things all around you, things you can see and touch and feel, that the rulebook cannot explain at all. That sounds impossible. How can our best theory of reality, the one that nails every experiment, also be full of holes? The answer is that the Standard Model is like a map of a city that draws every street in perfect detail, then stops dead at the edge of town. Inside the lines, flawless. Step 1 foot past them, and the page goes blank. So where are those blank spaces? They hide in plain sight. They hide inside a heavy cousin of the electron that spins slightly wrong. They hide inside ghostly particles that pour through your body by the trillion every second. They hide in the fact that the universe is stuffed with invisible stuff that outweighs every star, planet and person combined, roughly 5 times over. The rulebook has no page for any of it. Over the next parts, we are going to walk to the edge of the map and keep going. We will track down each crack, one at a time, and each one will be stranger than the last. Some are locked down by hard experiments and proven beyond doubt. Some are still guesses that keep brilliant people awake at night. A few might be the first faint hints of a deeper hidden rulebook we have not learned to read yet. But we should start with the biggest hole of all. It is so obvious that almost nobody ever stops to think about it. It is acting on you at this exact second, pinning you to your seat, holding the moon in the sky, spinning entire galaxies into slow, glowing wheels. It is the most familiar force in your entire life. You have felt it every moment since the day you were born. And the universe's rulebook does not contain a single working line about how it truly does its job. Drop your phone, and you already know what happens next. It falls. Gravity grabs it and pulls it straight to the floor. You have trusted that force your whole life. It holds your feet to the ground, keeps the oceans in their basins, and swings the planets around the sun in neat, endless loops. So here is a fact that should stop you cold. Gravity is missing from the rulebook. The Standard Model, our best theory of everything small, does not truly contain the force you feel most. The book handles 3 forces beautifully. There is electricity and magnetism, which lights your screen and sticks a magnet to your fridge. There is the strong force, which glues the centers of atoms together. There is the weak force, which powers the sun and certain kinds of radioactivity. Each one has a messenger particle, a tiny carrier that passes the force along, and the math for all 3 is rock solid. Gravity has no such working entry. Scientists have a name ready for its messenger, the graviton, but no one has ever caught one, and no one is sure they ever will. Worse, when physicists try to force gravity into the same quantum math that runs the rest of the book, the equations explode. Numbers that should stay small race off to infinity. The page fills with nonsense. We actually have a gorgeous theory of gravity. Albert Einstein wrote it more than 100 years ago, and it describes bending space around stars with stunning accuracy. The trouble is that Einstein's gravity and the Standard Model refuse to shake hands. One rules the world of the huge galaxies and black holes. The other rules the world of the tiny quarks and electrons. Put them in the same room, and they contradict each other. Now for the strangest twist. Of the four forces, gravity is by far the weakest. That feels absurd since it can crush a star. But think about a small fridge magnet. It can pick up a paperclip, lifting it against the pull of the entire planet. A magnet you could hide in your fist beats the whole Earth. Compared with the other forces, gravity is almost laughably feeble, and no one knows why it is so faint. So we are left with a bizarre situation. The force that shapes the biggest structures in the cosmos, the one steering whole galaxies, is the one our finest rulebook cannot write down. It sits outside the map entirely. You might expect the holes in the book to only show up out there, far away, in exotic places we can barely reach. Black holes, the edge of the universe, the first instant after the Big Bang. And gravity does live in those wild places, but the next crack is different, and in a way it is more unsettling. It does not hide in some distant corner of space. It shows up in a single, ordinary particle that the rulebook knows extremely well. A particle scientists can make by the millions, trap in a magnetic ring, and study up close in a lab. They know almost everything about it. They can predict how it should behave down to a level finer than counting the seconds in the age of the universe. And when they actually watched it move, it wobbled the wrong way. In a ring of magnets on the flat plains of Illinois, a tiny particle is spinning, and it is spinning slightly wrong. That particle is the muon, and its small mistake may be one of the loudest clues we have. A muon is like an electron's bigger, heavier cousin. It carries the same charge and behaves in many of the same ways, yet it weighs about 200 times more. It is also fragile. Left on its own, a muon survives for barely 2/millionths of a second before falling apart. To study one, you have to make it, use it, and read it fast. Here is the useful trick. A muon acts like a tiny spinning magnet. Drop it into a strong magnetic field, and it wobbles, the way a spinning top leans and circles as it slows. The speed of that wobble is something the rulebook predicts with jaw-dropping precision. The Standard Model can tell you the number to more than 10 decimal places. Why so exact? Because empty space is never truly empty. Around the muon, ghostly particles flicker in and out of existence, appearing for the tiniest sliver of time and vanishing again. This constant fizz tugs on the muon and nudges its wobble. The book claims to know every particle in that fizz, so it can add up every nudge and hand you a final answer. For years, scientists at a lab called Fermilab put that answer to the test. They built a giant ring, sent muons racing around it billions of times, and measured the wobble as carefully as anyone ever has. Their final result landed in 2025, pinned down to a few parts in a billion. To picture that sharpness, imagine measuring the distance across the United States and being sure of it down to the width of a few human hairs. And the measured wobble did not quite match the old prediction. The gap was small, almost impossibly small, but it was there. That gap set the physics world buzzing. Because if the muon wobbles faster than the known fizz can explain, then maybe the fizz contains something extra. Some unknown particle, absent from the rulebook, quietly tugging on the muon as it flies. A hidden ingredient. A brand new piece of nature betraying itself through the faintest wobble of a particle that lives for 2/millionths of a second. For a while, this looked like the crack, the first solid proof that the Standard Model was breaking. Newspapers ran the story, physicists let themselves hope. A tiny cousin of the electron spinning off the rules seemed ready to crack the whole book wide open. Then something happened that almost nobody outside the field expected. The measurements stayed rock solid, run after run, year after year. That side of the story only grew stronger. The problem came from the other side, from the prediction itself. because it turns out the hardest part of this whole puzzle was never catching the muon. It was calculating what the answer should have been in the first place, and when a group of scientists went back and recalculated it a completely different way, using some of the most powerful computers on Earth, the mysterious gap began to shrink. The proof that had everyone so excited started slipping through their fingers. The muon's tiny wobble had an enemy nobody saw coming. That enemy was the prediction itself. Remember, this puzzle has two sides. On one side sits the measurement, what the muon actually does in the ring. On the other sits the theory, what the rulebook says it should do. A crack only appears if those two numbers disagree. The measurement grew sharper and steadier every year, so the whole mystery came down to trusting the prediction, and the prediction turned out to be shockingly hard to pin down. The trouble lives in that fizz of ghostly particles around the muon. Most of that fizz is easy math. One slice of it is a nightmare. It involves the strong force, the same force that glues atoms together, and the strong force is famously messy to calculate. For that one stubborn slice, scientists needed another way in. For years they used a clever shortcut. They took real data from other experiments, older machines that smashed particles together, and used those measurements to estimate the messy part. That approach gave a prediction that disagreed with the muon ring. That disagreement was the exciting gap. Then a second group tried something bolder. Instead of borrowing old data, they built the whole messy slice from scratch inside a supercomputer. They simulated the strong force directly, crunching numbers for months on machines that can do quadrillions of calculations every second. This method has a name, lattice, because it chops space into a fine grid, like graph paper stretched over reality. And the supercomputer answer came out different. It pushed the prediction closer to what the muon ring actually measured, close enough that the exciting gap nearly vanished. So now physicists face an awkward split. Two respected ways of calculating the same number give two different answers. One keeps the mystery alive, the other quietly erases it. The measurement is trusted by everyone. The theory is at war with itself. Picture two master chefs handed the exact same recipe. One tastes the dish and says it needs salt, the other tastes it and says it is perfect. They cannot both be right, and until they agree, no one can say whether the meal is broken. Right now, the honest answer is that we do not know. The muon might still be pointing at hidden physics, a secret particle lurking in the fizz, or the whole thing might dissolve into a math disagreement that gets sorted out in a few years. Scientists are working flat out to settle it, comparing methods, hunting for mistakes, running the numbers again. This is what real discovery looks like up close. Messy, slow, full of brilliant people who cannot yet agree. The muon has not confessed. It is still sitting in that ring, wobbling, keeping it secret. While one team argued over the muon, a different machine thousands of miles away dropped a bombshell of its own. This time, the trouble was not a faint wobble measured to a billionth. This time, a particle appeared to break the rules in a much heavier, much blunter way. It came down to weight. Scientists took one of the most important particles in the book, the carrier of the weak force, and simply weighed it. The book said it should tip the scale at one number. The machine read a different, larger number, and the size of that surprise sent a shock through all of physics. A detector at Fermilab weighed a single particle, and the answer that came back should have been impossible. The particle was the W boson, and its weight refused to match the rulebook. The W boson is a heavy hitter. It carries the weak force, the one that lets the sun burn and drives certain kinds of radioactive decay. It is far chunkier than a proton, and its exact weight is woven deep into the math of the standard model. The book does not leave that weight open. It ties the W boson's mass to other known numbers so tightly that scientists can predict it and check whether nature agrees. In 2022, a team running an experiment called the Collider detector at Fermilab announced their result. They had spent years measuring the W boson from a huge pile of old collision data, and their answer came out heavier than the rulebook allowed, not by a hair, by an amount so large it stunned the field. How large? Physicists measure surprise in units called standard deviations. 1 or 2 is a shrug, easily explained by luck. 3 starts to raise eyebrows. This results at 7 standard deviations away from the prediction. To feel that, imagine flipping a coin and having it land perfectly on its edge, then doing it again and again and again. A result that far out almost never comes from chance. If the measurement was right, The meaning was enormous. A W boson that weighs too much would be a fingerprint. It would suggest that unknown heavy particles are hiding in that quantum fizz, subtly dragging the W boson's weight upward. Another crack, another whole set of missing pages waiting to be written. The whole community turned to look, and that is exactly how science is supposed to work, because a claim this big cannot stand on one experiment alone. Other teams had to weigh the W boson too, on different machines with different methods, and see if the shock held up. The main check came from the Large Hadron Collider, the giant ring under the border of France and Switzerland, the most powerful particle smasher ever built. Its compact muon solenoid team sifted through more than 1 billion collisions and weighed the W boson with their own careful method. Their answer landed right where the rulebook said it should. Normal. Ordinary. No shock at all. So now there is a standoff. One respected experiment reports a W boson that breaks the rules by a mile. Several others report a W boson that behaves perfectly. They cannot all be correct. Most physicists now lean toward the idea that the surprising result hides some subtle mistake, a systematic error buried in a mountain of tricky data. But the team that found it stands by their work, and the disagreement is still open. Two of the loudest alarms in modern physics, the muon and the W boson, have both grown quieter under closer inspection. That is a little deflating. It might feel like the rulebook is winning, but some cracks cannot be explained away, argued down, or blamed on a bad calculation. Some are locked in, confirmed, carved in stone. And the clearest one of all comes from the faintest, strangest particles in the entire universe. Particles so shy that trillions are blasting through your body right now, and the rulebook swore they should weigh absolutely nothing. Right now, as you breathe, trillions of tiny particles are flying straight through your body, and almost none of them touch a thing. They are called neutrinos, and they carry a secret that the rulebook got flatly wrong. Neutrinos are the ghosts of the particle world. They are unbelievably light, they carry no electric charge, and they barely interact with anything at all. They stream out of the sun in unthinkable numbers, race across space, and pass through planets as if solid rock were open air. A neutrino could fly through a wall of solid lead stretching for light years and have a decent chance of coming out the other side untouched. When physicists first wrote the Standard Model, they made a clean, simple choice about these ghosts. They set the neutrino's weight to exactly 0, massless. It made the math tidy, and for a long time nothing pushed back. Every experiment seemed fine with weightless neutrinos. Then the ghost betrayed the book. Careful experiments, run deep underground to hide from noise, showed that neutrinos have mass after all. A tiny, whisper-thin mass, but a real one. This is confirmed. It is locked down. Scientists were so sure of it that the discovery won the Nobel Prize in 2015. The rulebook's clean assumption that neutrinos weigh nothing is simply false. Now, the mass is almost comically small. A neutrino is at least 1 million times lighter than an electron, and the electron is already one of the lightest things we know. If an electron were the weight of a single grape, a neutrino would be lighter than a speck of dust drifting off that grape's skin. Yet lightweight and weightless are worlds apart. 0 is a special number. The moment a neutrino tips the scale, even a hair above 0, the book has a hole in it. This might sound like a small correction, a minor patch. It is anything but. The way the Standard Model is built, there is no natural room for a neutrino mass. Adding 1 is like discovering that a wall you thought was solid has a hidden door in it. Now you have to ask what is on the other side and who put the door there. That tiny mass forces open some of the deepest questions in all of science. Where does the weight even come from? Neutrinos might get their mass in a completely different way from every other particle, through a mechanism the book never described. Some scientists suspect the ghosts borrow their weight from a realm of undiscovered heavy particles, giants far too massive for any machine we have ever built to reach. If that is true, the faint little ghost in front of us is quietly tied to monsters we have never seen. Either way, the door leads somewhere entirely new. And here is the part that still amazes me. Scientists did not find the neutrino's mass by putting 1 on a scale. You cannot catch a ghost and weigh it. They found it by watching neutrinos perform an impossible-looking magic trick in mid-flight. a trick that only works if the particle has weight. Fire one kind of neutrino across a great distance, and by the time you catch it at the other end, it has transformed into a different kind entirely. It changes its identity as it travels. For decades, this shape-shifting confused everyone, right up until scientists realized it was the smoking gun. Neutrinos come in 3 flavors, and the strangest thing they do is switch flavors while flying through empty space. Fire one type into the dark, catch it far away, and it has quietly become another. That single trick shattered the old rulebook. Let me set the scene. Neutrinos come in 3 kinds, tied to 3 heavier particles. There is the electron neutrino, the muon neutrino, and the tau neutrino. For a long time, scientists assumed a neutrino kept whatever flavor it was born with, from birth to death. The sun cracked that assumption open. The sun is a neutrino factory, blasting out electron neutrinos as it burns. Scientists calculated how many should reach Earth, built detectors, and started counting, and they kept coming up short. Only about a third of the expected electron neutrinos showed up. 2 out of every 3 had gone missing. This became known as the solar neutrino problem, and it haunted physics for years. Where were the missing ghosts? Was the sun behaving strangely? Were the detectors broken? The real answer was stranger than either. The neutrinos were not missing. They had changed. On the long trip from the sun to Earth, many of those electron neutrinos morphed into muon neutrinos and tau neutrinos, flavors the early detectors could not see. The count looked short only because the detectors were watching for one flavor, while the particles kept swapping between all 3. The proof came from a huge tank of ultra-pure water buried deep under a Japanese mountain, wrapped in thousands of sensitive light detectors. Called Super Kamiokande, it could catch the faint flashes neutrinos make, and finally track this shape-shifting directly. The switching was real, and it happened over and over. Here is the beautiful part, the reason this matters so much. A particle can only pull off this flavor-switching trick if it has mass. If neutrinos truly weighed nothing, they would be locked into one flavor forever, frozen, unable to change. The very act of shape-shifting proves they carry weight. Nature handed us the answer by making the ghost dance. Think of it like a musical chord travelling through the air. 3 notes are blended together inside every neutrino. As it flies, those notes drift in and out of step, so the chord you hear at the end sounds different from the one that started. The particle is always a mix. What changes is which flavour rings out loudest when you finally listen, so the missing solar neutrinos were never lost, they were disguised. And their disguise is airtight proof that the rulebook's neutrinos, the weightless ones, do not exist in the real universe. This is not a disputed wobble or a lonely measurement. Many experiments on different continents, catching neutrinos from the sun, from the sky, from nuclear reactors, all tell the same confirmed story. But every answer in this field seems to unlock a harder question. We now know the 3 neutrinos have 3 slightly different weights. We can even measure the gaps between them, how much heavier one is than another. Yet there is something basic we still cannot figure out, something you would think would be simple. We do not know their order. We cannot yet tell which neutrino is the heaviest and which is the lightest. And that missing piece of knowledge reaches all the way back to the birth of the universe. We know the 3 neutrinos have 3 different weights. We just cannot figure out which one is heaviest. It sounds almost too simple to be a real mystery, and yet it has resisted the sharpest minds in physics for years. Here is the strange situation. Those flavor-switching experiments were powerful, but they had a limit. They could measure the gaps between the neutrino weights, how far apart the 3 masses sit, but they could not reveal the actual order. It is a little like being told the height differences between 3 siblings, without ever being told which one you're looking at. You know one pair differs by a lot and one pair by a little. You still cannot line them up. That leaves 2 possible arrangements, and scientists have plain names for them. In the first, you have 2 lighter neutrinos close together and one heavier one sitting well above them, like a tall kid towering over 2 shorter friends. In the second, the picture flips, with 2 heavier ones near the top and a single light one hanging below. One of these is the truth. We do not yet know which. To settle it, scientists are building enormous new detectors, some buried more than a mile underground to block the constant rain of cosmic particles from above. A few will fire beams of neutrinos hundreds of miles straight through the solid Earth, from one lab to another, catching how the beam shifts along the way. The rock does not slow neutrinos down at all. To a neutrino, the whole planet is nearly transparent. You might wonder why anyone should care about the order of 3 featherweight ghosts. The answer is that this tiny detail is wired into the biggest questions we have. The neutrino masses may hold clues about how particles got their weight in the first place, and even about why the universe filled up with matter instead of empty light. Get the order right, and you tighten the screws on theories that try to explain the whole cosmos, and the weights are almost unbelievably small. Even the heaviest neutrino is still so light that scientists have not managed to measure its exact weight at all. They know only that it is there, hovering just barely above nothing. Picture trying to weigh a single grain of pollen using a bathroom scale built for people. That is the kind of challenge we're talking about, except far, far harder. So the neutrino keeps its secrets. We proved it has mass. We proved it shapeshifts. We measured the gaps. And we still cannot answer the childlike question of which one is biggest. The Rulebook, which never expected these particles to have any weight at all, offers no help whatsoever. There is one more neutrino mystery, and it may be the deepest of them all. It cuts to the heart of what matter even is. Every particle of ordinary matter has an opposite, a mirror twin made of antimatter, carrying the reverse electric charge. An electron has its opposite, a proton has its opposite. When a particle meets its twin, both vanish in a flash of pure energy. But the neutrino has no charge to flip, and that raises a question so strange it borders on impossible. What if a neutrino is its own opposite? What if the ghost and its mirror twin are one and the same particle? Every particle of matter has an antimatter twin, its exact opposite, and when the two meet, they destroy each other in a burst of light. But the neutrino may be hiding the weirdest secret in physics. It may be its own twin. Let me explain why that is even thinkable. Antimatter is real, and it is simple to describe. For most particles, the antimatter version is identical in almost every way, except the electric charge is flipped. The electron is negative, so its twin, the positron, is positive. Bring them together and they annihilate, converting their entire mass into energy in an instant. Now look at the neutrino. It has no electric charge to flip. It is neutral, blank, balanced. So when you try to build its antimatter twin, you run into a puzzle. If the only real difference between a particle and its opposite is charge, and the neutrino has no charge, then maybe there is no difference at all. Maybe the neutrino and the antineutrino are secretly the same thing, wearing two masks. Physicists have a name for a particle like that, one that is its own opposite. They call it a Majorana particle, after the scientist who first dreamed it up, and whether the neutrino is one of these could rewrite our understanding of matter itself. How do you test something so slippery? You go hunting for one of the rarest events in nature. Deep underground, scientists watch certain rare atoms that can undergo a strange kind of radioactive decay. Normally when this decay happens, it should spit out two neutrinos along with everything else. But if the neutrino really is its own twin, those two neutrinos could cancel each other out inside the atom and disappear entirely, leaving a telltale signature behind. That vanishing neutrino event has a mouthful of a name, but the idea is simple. Two ghosts meet, recognize each other as twins, and erase themselves. If it happens even once, cleanly, it proves the neutrino is its own antimatter. The catch is that this decay, if it happens at all, is almost unimaginably rare. Detectors sit in silence for years, waiting for a single flash that may never come. To have any hope, scientists bury them far below the surface, under mountains of rock, to block out the noise of ordinary radiation. Then they wait, and wait. So far no one has caught it. The search continues in labs around the world, each one a little more sensitive than the last, each one straining to hear a whisper that may or may not be there. And the stakes could hardly be higher. If the neutrino is its own twin, it opens a possible path to answering the greatest question of all, why there is any matter in the universe at all. A self-twinning neutrino, active in the first moments after the Big Bang, could have tipped the scales toward matter and away from empty light. everything you see could trace back to that single strange property of the ghost particle. We will come back to that grand question soon, because it is the beating heart of this whole story. But first, there is a smaller, closer puzzle that shows how deep our confusion goes. It does not involve exotic ghosts or antimatter twins. It involves the plain, familiar neutron, one of the particles inside every atom of your body. And that ordinary particle cannot even agree with itself on how long it lives. Take a neutron out of an atom, set it loose on its own, and it will fall apart in about 15 minutes. That much everyone agrees on. The problem is that when scientists measure exactly how long, they get two different answers, and the two refuse to meet. The neutron is one of the most ordinary particles there is. Along with the proton, it sits in the center of nearly every atom in you, in this planet, in the stars. Locked inside a nucleus, a neutron is stable and can last essentially forever. But pull one out and let it drift free, and it becomes unstable. After a short while it decays, breaking into a proton and a couple of other particles. Timing that decay sounds like a simple job. It is not. Scientists measure the free neutron's lifetime in two very different ways, and the methods have earned nicknames. The first is the bottle. You gather up slow, cold neutrons and trap them in a container, sometimes using magnetic fields so they never even touch the walls. You wait a set time, then count how many neutrons are still there. Fewer survivors means faster decay, and from that you work out the lifetime. The second method is the beam. Here you send a steady stream of neutrons flowing through a chamber, and instead of counting survivors, you count the wreckage. Every time a neutron decays, it leaves a trace, and by counting those traces against the flow, you get the lifetime a completely different way. Two methods, one particle, one number. They should agree. They do not. The bottle experiments land on a lifetime of about 878 seconds. The beam experiments land on about 888 seconds. That is a gap of roughly 10 seconds. It sounds tiny, almost silly next to a 50-minute lifetime, but both methods have been refined for decades, and both are now so precise that 10 seconds is a canyon. The gap is far bigger than the errors either side admits. Physicists measure how serious a disagreement is, and this one now sits around 5 standard deviations apart. That is the gold standard line, the same level of certainty scientists demand before announcing a genuine discovery. So this is a real, sharp, stubborn split between two careful measurements of one everyday particle. What could cause it? One dull possibility is that some hidden mistake lurks in one method, a subtle error no one has spotted. Teams have hunted hard for such an error and mostly come up empty. The other possibility is thrilling. Maybe the neutron sometimes decays down a secret path the rulebook never listed. Maybe, once in a while, a neutron falls apart into something invisible, something the beam catches by its absence but the bottle counts as a survivor. Some scientists have wondered whether that invisible escape route could even be linked to the dark, unseen matter filling the cosmos. As of now, the puzzle is wide open. New experiments are running, using fresh methods with different weaknesses, trying to break the tie. The neutron, one of the humblest bricks of reality, is keeping its own lifespan a secret. And that 10-second gap, small as it seems, ties directly into the single biggest question a person can ask. Not why the neutron dies, but why anything is here to die at all. The universe should be empty. According to the rulebook, the Big Bang should have left behind nothing but light, a vast, dark, lifeless glow with no stars, no planets, and no you. Yet here we all are. Explaining that is one of the deepest problems in science. Here is the trouble. When energy turns into matter, and the early universe was overflowing with energy, it always makes matter and antimatter in equal pairs. For every particle, an antiparticle. They come into being together, perfectly balanced. And as we saw when a particle meets its antimatter twin, both annihilate instantly, vanishing into a flash of pure light. So run the Big Bang forward in your mind. The infant universe fills with equal amounts of matter and antimatter. Almost immediately, every particle finds its twin, and they wipe each other out. The whole cosmos should have flashed into radiation and gone dark, a perfectly balanced act of mutual destruction leaving nothing solid behind. That is not what happened. Somehow matter won. A little extra matter survived the Great Annihilation, and that leftover scrap became everything. Every galaxy, every star, every atom in your fingertips is made of that tiny surplus. How tiny? For every billion pairs of matter and antimatter that formed and destroyed each other, only about one extra particle of matter was left standing. Picture 1,000,001 particles of matter meeting 1,000,000,000 particles of antimatter. The billion pairs annihilate in a blaze of light, and that single, lonely leftover walks away. Multiply that survivor across the whole universe, and you get all the matter there is. We are the rounding error of a cosmic accident. But why was there any surplus at all? Why did matter get even that razor-thin edge? For the books to balance, matter and antimatter must behave just slightly differently from each other. The mirror between them has to be flawed, ever so slightly, so that reactions favour matter by a hair. The rulebook does contain a small flaw in that mirror. Scientists have known for a long time that matter and antimatter are not perfect reflections. In a few rare reactions they act differently, and that difference is real and confirmed. So the ingredient exists. The problem is the amount. The flaw the standard model allows is far too weak. Feed it into the equations, and it produces nowhere near enough surviving matter to build a universe. It falls short by a staggering margin, missing the mark so badly that entire galaxies are left completely unexplained. Something else, some deeper source of imbalance the book does not know about, must have tipped the scales in those first fractions of a second. For decades, scientists have hunted for cracks in that mirror wherever they could find them, testing particle after particle, looking for matter and antimatter parting ways. Every new crack is a clue. Every new crack is a place where the missing physics might be hiding. And in 2025 they found a fresh one, in a place no one had ever seen it before. For the first time, scientists caught antimatter breaking the mirror in the very family of particles that builds ordinary matter, the same family your protons and neutrons belong to. It was a genuine milestone, a brand new window into why we exist at all. For the first time in history, scientists watched matter and antimatter break their mirror inside the building blocks of ordinary stuff. It happened in 2025, and it cracked open a door that had stayed shut for 60 years. To understand why this mattered so much, remember the setup. Matter and antimatter are supposed to be perfect reflections of each other, but the mirror has a flaw, and finding that flaw is one of the great goals of physics, because it may explain why the universe holds anything at all. Scientists had spotted the flaw before, but only in one family of particles. Particles come in two broad families. There are mesons, made of a quark paired with an antiquark, a two-piece particle, and there are baryons, made of three quarks bound together. This second family is the important one, because baryons are what you are made of. Every proton and every neutron in your body is a baryon. The visible universe, all the matter you can see and touch, is built from baryons. Way back in 1964, scientists first caught matter and antimatter behaving differently, and they caught it in mesons. That discovery was huge, and it kept happening in meson after meson over the years. But baryons, the family that actually builds us, stayed silent. Every attempt to catch them breaking the mirror came up empty. For 60 years, the building blocks of ordinary matter kept a perfectly straight face. Then came the LHCb experiment, a detector on the Large Hadron Collider built to study exactly these kinds of particles. The team focused on a heavy, short-lived cousin of the proton called the Beauty Lambda baryon. It is made of three quarks, like a proton, but one of them is a rare, heavy quark called Beauty. They compared how this particle decays with how its antimatter version decays, sifting through mountains of collision data. And the two did not match. The matter version and the antimatter version fell apart at slightly different rates. The difference came out to about 2.5%, small but unmistakable, and it reached the gold standard of certainty that physicists demand before they will call something a discovery. This was real. Matter and antimatter behave differently inside baryons, and now we've seen it with our own instruments. It was the first time ever, 60 years of searching, and finally the building blocks of the everyday world showed their hidden asymmetry. Scientists around the world called it a milestone, a brand new avenue for testing the rulebook and hunting for whatever lies beyond it. A fresh crack in the mirror in exactly the family of particles that matters most for explaining our existence. For a moment, it might feel like the answer is within reach. We know matter beat antimatter. We know the mirror is flawed. And now we have caught that flaw in our own kind of matter. Surely the puzzle is close to solved. It is not. Because when scientists take every known crack in the mirror, including this shiny new one, and add them all together, the total still comes up catastrophically short. All the imbalance we can find, combined, is nowhere near enough to explain a single galaxy, let alone a whole universe full of them. Add up every crack in the mirror between matter and antimatter that scientists have ever found, and the grand total is still about 1 billion times too small to explain why you exist. That gap is one of the loudest silences in all of physics. Let me lay it out plainly. To build a universe made of matter, the early cosmos needed a certain amount of imbalance between matter and antimatter. Scientists can calculate roughly how much was required to leave behind all the galaxies we see. They can also add up all the imbalance the rulebook actually allows, every confirmed crack in the mirror, including the brand new one just found in baryons. Then they compare the two numbers. The two numbers are not close. The imbalance the standard model permits falls short of what the universe demands by a factor of around 1 billion. It is a chasm, not a gap. Picture trying to fill a full-size swimming pool using a single eyedropper. You squeeze and squeeze, one drop at a time, and the water level barely twitches. That is roughly how far the known physics falls short of explaining the matter around you. The rulebook's mirror is flawed, yes, but nowhere near flawed enough. Its tiny imperfection could never have tipped a whole universe toward matter. So what does that leave us with? A confirmed problem and a missing answer. We know for certain that matter won. We are the living proof, made entirely of the survivors, and we know for certain that the rulebook cannot explain the victory. The math simply does not reach. Something else had to be at work in those first fractions of a second, some deeper, stronger source of imbalance that we have not yet discovered. Where is it hiding? Nobody knows for sure. Maybe it lives with those ghostly neutrinos and their possible self-twinning nature. Maybe it involves brand new particles that existed only in the searing heat of the newborn universe and then vanished forever. Maybe it points to a whole layer of physics beneath the rulebook, a hidden set of rules that briefly ruled the cosmos and left its fingerprints in the fact that we are here at all. This is why scientists keep hunting for every possible crack in that mirror, testing particle after particle, pushing their instruments to the edge of what is possible. Each new measurement is a chance to catch the missing imbalance in the act. So far, every crack they find, real as it is, only deepens the mystery, because none of them, alone or combined, is anywhere near big enough. It is a humbling thought. The most basic fact about the universe, that it contains something rather than nothing, sits outside our best theory of reality. We exist, and our finest rulebook cannot say why. And here is where the story truly opens up. Because the matter we have been fighting to explain, all the protons and neutrons and atoms, all the stars and planets and people, turns out to be only a thin sliver of what fills the universe. When astronomers weigh the galaxies, they find something far heavier lurking in the dark, something invisible, something the rulebook does not contain even a single word about. And there is roughly 5 times more of it than everything we have discussed so far. When astronomers weigh a galaxy, the numbers do not add up, and the mismatch is enormous. Galaxies spin so fast that, by all the rules we know, they should be tearing themselves apart. Something invisible is holding them together, and there is a staggering amount of it. The first hints came almost a century ago. In the 1930s, an astronomer noticed that galaxies in a distant cluster were racing around far too quickly for the visible matter to keep them bound. Decades later, in the 1970s, an astronomer named Vera Rubin measured how stars orbit within spinning galaxies, and she found the same shocking pattern, over and over. The stars at the edges were moving as fast as the ones near the centre, which should have been impossible. Think of a spinning merry-go-round. If you spin it too fast, the riders at the outer edge fly off. Galaxies spin fast enough that their outer stars should have flung themselves into deep space long ago. Yet the stars stay put, held in place by a grip far stronger than their visible matter could ever provide. Some unseen mass is doing the holding. Scientists call that unseen mass dark matter. The name simply means we cannot see it. It gives off no light. It blocks no light. It does not glow, shine, or cast a shadow. It slips through ordinary matter almost without a trace, gripping the universe only through gravity. You could be swimming through a sea of it this very moment and never feel a thing. Here is the number that should stop you. Dark matter is not some rare trace. There is roughly 5 times more of it than all the ordinary matter in the universe combined. Every star, every planet, every cloud of gas, every living thing, all of it together is outweighed 5 to 1 by stuff we cannot see. The glowing, visible cosmos we admire in telescope photos is the minority. We have been staring at the small part all along. And this is not a wild guess from one lonely measurement. Scientists have confirmed dark matter's presence through many separate methods that agree with one another. They watch how its gravity bends light from distant galaxies, warping space like a giant lens. They map the faint afterglow of the Big Bang and see dark matter's fingerprints stamped across the early universe. They model how galaxies form and find that, without dark matter, the cosmos we live in could never have come together at all. The evidence is overwhelming. Yet the rulebook contains nothing that fits. Not one of its 17 particles behaves the way dark matter must. It is real. It is everywhere. It outweighs everything we know, and the standard model does not have a single page for it. This is perhaps the largest, most glaring hole in the entire book. So the obvious next step is to figure out what dark matter is made of. If it is a particle, we should be able to catch one. Scientists have believed that for decades, and they have thrown extraordinary effort and cleverness at the hunt. They have built exquisite detectors, buried them deep underground, and waited with almost unbelievable patience for a single dark particle to reveal itself. And after 40 years of searching, that particle has never once shown up. For 40 years, scientists have hunted the particle that makes up dark matter, and it has never appeared. Not once. Some of the most sensitive machines ever built have sat in the dark, waiting, and the guest of honor has refused to arrive. For a long time, physicists had a favorite suspect. They imagined a new kind of particle, fairly heavy, that ignores almost every force and touches ordinary matter only on the rarest of occasions. A particle like that would drift through the universe unseen, gripping galaxies with gravity while brushing past everything else. It fit the clues so neatly that it became the leading candidate for decades. To catch one, scientists designed detectors of remarkable delicacy. The idea is simple to say and brutally hard to do. If dark matter is streaming through the Earth, then once in a great while, a dark particle should bump into the nucleus of an ordinary atom and give it a tiny kick. Build a detector sensitive enough, and you might catch that faint nudge. The trouble is that the ordinary world is full of noise. Cosmic particles rain down from space. Natural radiation seeps from the rocks. All of it can fake the signal you're looking for. So scientists bury their detectors deep underground, beneath mountains or down old mine shafts, using a mile or more of solid rock as a shield. Then they cool their instruments to near the coldest temperature possible, and watch, sometimes for years, for a single clean bump. And the bumps have not come. Detector after detector, each one larger and more sensitive than the last, has stared into the dark and found nothing convincing. Every time scientists build a machine powerful enough to catch their favourite particle, and it comes up empty, they cross another hiding place off the map. The favourite suspect is running out of shadows to hide in. That silence is its own kind of clue. It is pushing scientists to rethink what dark matter even is. Maybe it is not a heavy, shy particle at all. Maybe it is something far lighter, a ghostly wisp millions of times fainter than anyone first guessed. Some scientists now chase a feather-like candidate so small it would behave almost like a wave washing through the cosmos. Others wonder whether dark matter is a whole hidden family of particles, a shadow world with its own rules tangled up with ours only through gravity, so we are left in a strange and humbling place. Dark matter is real. The evidence for it is rock solid, confirmed from many directions. It outweighs everything we can see by 5 to 1, and after 4 decades of brilliant patient searching, we still have no idea what it is made of. The largest reservoir of matter in the universe is a complete blank in our rulebook, and it is guarding its identity fiercely. If that were the only great unknown filling the cosmos, it would be plenty. But dark matter is only the second biggest mystery out there. There is something else, something even more abundant, something that does far more than quietly hold galaxies together. This other thing is actively pushing the entire universe apart, faster and faster with every passing moment. And when astronomers first stumbled onto it, they did not believe their own eyes. In the late 1990s, two teams of astronomers set out to measure how fast the universe is slowing down, and they discovered it is speeding up instead. That result was so strange that both teams spent months trying to prove themselves wrong. Here is what they expected. The universe has been expanding ever since the Big Bang, with all its galaxies flying apart. Gravity, the great cosmic brake, should be tugging on all that matter and gradually slowing the expansion down. The only real question, they thought, was how much. Maybe the universe would coast forever, slowing gently. Maybe gravity would eventually win and pull everything back together. Either way, the expansion should be losing steam. To measure it, the teams tracked a special kind of exploding star, a stellar blast that always shines with nearly the same true brightness. Because these explosions are so predictable, astronomers can use them as cosmic mile markers, judging distance by how bright or faint they appear. By studying explosions across billions of light years, the teams could chart how the universe's expansion had changed over cosmic time. The answer floored them. The distant explosions were fainter than they should have been, meaning they were farther away than a slowing universe could explain. The expansion was not breaking at all, it was accelerating. Space itself was flying apart faster and faster, as if some invisible pressure were pushing it outward and growing stronger by the eon. Scientists gave that invisible pressure a name: dark energy. And unlike dark matter, which pulls things together, dark energy pushes space apart. It behaves like a kind of anti-gravity woven into the fabric of empty space itself. The more space there is, the more dark energy there seems to be, and the harder the push becomes. Now brace yourself for the numbers, because they rearrange your whole sense of the cosmos. Dark energy makes up about 68% of everything in the universe. Dark matter, the invisible stuff holding galaxies together, makes up about 27%. And ordinary matter, everything you have ever seen or touched, every star, every planet, every atom in your body, adds up to only about 5%. Let that settle. All the glowing galaxies, all the light in the night sky, all of chemistry and biology and rock and water and life is a mere 5% of what fills reality. We are the thin froth on top of a dark, unknown ocean. 95% of the universe is made of things the rulebook cannot name. And dark energy is the biggest slice of all. It is the dominant ingredient of the cosmos, the force steering its ultimate fate, and the standard model does not contain a single line describing it. It sits entirely outside the map, off the edge of the page, ruling the universe from the dark. You might think the least scientists could do is estimate how much dark energy there ought to be. There is one obvious source of energy hidden in empty space itself, and the math to calculate it already exists. So physicists rolled up their sleeves and worked it out. The answer they got was wrong. Wildly, catastrophically, almost comically wrong. In fact, it stands as the single worst prediction ever made in the history of science. Physicists once tried to calculate how much energy is hidden inside empty space, and their answer was too large by a 1 followed by 120 zeros. It is the worst prediction in the history of science, and it comes from our best theories working exactly as designed. Start with a fact that sounds like fantasy but is confirmed. Empty space is not truly empty. Down at the smallest scales, the quantum rules say that space constantly fizzes with particles popping into existence and vanishing again, faster than any blink. These flickering particles are real. Their effects have been measured in the lab. Empty space is a boiling, restless sea, even in the deepest void between the stars. All that fizzing should carry energy. And energy, according to our understanding, pushes on space. So here was a tempting idea. Maybe the energy of empty space is the dark energy driving the universe apart. The pieces seemed to fit. Scientists had a mystery, dark energy, and a natural candidate, the energy of the quantum void. All that remained was to calculate the amount and check the match. So they calculated it. They added up the energy the fizzing void should contain, using the same trusted rules that get so many other answers right. And the number that came out was absurd. It was larger than the amount of dark energy we actually observe by a factor so vast it defies imagination. A 1 with 120 zeros trailing behind it. There is no ordinary comparison big enough to hold that gap. Let me try anyway. Imagine you predicted that a single raindrop would fall, and instead an ocean crashed down. An ocean so enormous it could swallow every star in every galaxy in the observable universe many times over. Even that wild picture does not stretch far enough. The mismatch between the predicted energy of empty space and the real dark energy is the largest disagreement between theory and reality that scientists have ever produced. So what does that mean? It means our finest rules, applied honestly to a simple question, give an answer that is catastrophically, impossibly wrong. The universe clearly does not contain that ferocious ocean of energy. If it did, space would have been ripped to shreds long before any galaxy could form, and we would not be here. So something must be cancelling almost all of that energy, wiping it out with breathtaking precision, leaving behind only the faint whisper we call dark energy. What does the cancelling? Nobody knows. It would have to be a balancing act so exact that it neutralises a monstrous number down to almost, but not quite, 0, and leaves exactly the right sliver behind. That level of fine balance looks less like an accident and more like a rule we have not discovered, a missing piece of the book, hiding in the emptiest place imaginable. It is a stunning thought. The void between the stars, the nothing that fills most of reality, holds a mystery deep enough to break our best physics. Empty space is trying to tell us something, and we cannot yet read the message. And if empty space is this strange, then the particle that gives that space its texture becomes even more suspicious. The Higgs boson, the last piece the rulebook found, carries a puzzle of its own. By every reasonable expectation, it should not be nearly as light as it is. And that oddly gentle weight hints that our universe may be balanced on the edge of a knife. The Higgs boson is far too light, and that single fact keeps physicists awake at night. The rulebook found this particle last in 2012, and it should be one of the heaviest things in nature. Instead, it came out shockingly gentle, and no one can explain why. Start with what the Higgs does. It is the reason other particles have weight at all. Picture an invisible field filling all of space like a thick syrup. As particles move through it, they feel a drag, and that drag is what we call mass. The Higgs boson is a ripple in that syrup, so the Higgs is the giver of weight, the source of mass for much of the particle world. Here is the problem. The Higgs has its own weight, and the rulebook says that weight should be dragged upward by the constant fizz of ghostly particles around it. The same fizz we met with the muon. Each flickering particle tugs on the Higgs and should pull its mass higher and higher, all the way up toward the scale where gravity itself takes over. By that logic, the Higgs ought to be almost unimaginably heavy. It is not. The Higgs is lighter than that natural scale by a factor of about 100,000 trillion. To picture that gap, imagine a number so large that writing it out would fill a line with 17 zeros. The Higgs sits that far below where it seems it should. For the Higgs to stay this light, a whole army of enormous tugs has to cancel out, almost perfectly. The pushes and pulls must balance to around 16 decimal places, leaving behind only the tiny weight we measure. That is like balancing a sharpened pencil on its point and having it stand there, unmoving for the entire age of the universe. Physicists call this the hierarchy problem, and it is one of the sharpest puzzles in the book. Why does nature bother with such a fussy, delicate balance? Nobody knows. Some scientists find it so unnatural that they are convinced a hidden mechanism must be holding the Higgs down, some new physics we have not yet found. Others wonder if the balance is simply a brute fact of our universe, with no deeper reason at all. The measurement is rock solid. The reason behind it is a complete blank. And this is where the story turns genuinely eerie. That precise weight of the Higgs, together with the weight of the heaviest known particle, the top quark, does more than set the mass of things. Together, those two numbers decide something far larger. They decide whether the very ground of reality, the empty space we all live inside, is truly stable. When scientists plug in the real measured values, the answer they get is deeply unsettling. Our universe does not appear to sit safely at the bottom of the valley in the most stable state possible. It seems to be perched a little way up the slope, resting in a shallow dip, balanced in a spot that looks calm but might hide a trapdoor beneath it. If that reading is right, then everything you know is sitting on a kind of cosmic ledge, and a ledge, no matter how still it looks, is a place you can fall from. Our universe may be sitting on a hidden trapdoor, and the key that decides whether it stays shut is the weight of two particles. When scientists measured them, the answer suggested that empty space itself might not be as safe as it looks. Let me explain the strange idea behind this. Think of empty space as a ball resting in a valley. A ball at the very bottom of a deep valley is stable. Nudge it, and it rolls right back to the bottom. That is what a truly stable universe would look like, settled in the lowest possible state, safe forever. But there is another possibility. Imagine the ball resting instead in a shallow dip partway up the hillside. It sits still, it looks perfectly calm, yet it is not at the true bottom. A big enough nudge could knock it out of the dip and send it tumbling down to a far lower place. Scientists have a name for a universe like that. They call it metastable, which means stable for now, but not truly permanently safe. When physicists take the measured weight of the Higgs boson and the measured weight of the top quark and feed them into the equations, our universe lands right on the edge between those two pictures. It sits astonishingly close to the boundary between a fully stable cosmos and a metastable one. And the reading leans just slightly toward metastable, toward the shallow dip on the hillside. Here is what that would mean, taken to its wild conclusion. Somewhere, someday, a tiny patch of space could randomly slip out of our shallow dip and drop into the true bottom. That patch would become a bubble of a new, lower kind of empty space. And that bubble would expand outward at the speed of light, swallowing everything it touched, rewriting the laws of physics inside it as it grew. Stars, planets, atoms, all of it, erased and remade under new rules. Now, before you panic, breathe. The math also says this is fantastically unlikely to happen anytime soon. The wait would be far, far longer than the current age of the universe, longer than almost any number that means anything to a human mind. You are in no danger. Your descendants 1 billion years from now are in no danger. The unsettling part is not the threat, it is the balance. Why should our universe sit so precisely on that knife's edge, hovering right at the border between safe and doomed? It could have landed comfortably in the deep, stable valley. It could have landed hopelessly in the unstable zone. Instead, it sits almost exactly on the line, and the rulebook offers no reason at all for that razor-fine placement. It starts to feel like a pattern. The Higgs is tuned to a hair. The stability of space is tuned to a hair. Over and over, our universe seems balanced on impossibly fine points, with no explanation for why. That pattern goes deeper than weight and stability. It reaches into the very structure of matter, into the number of ingredients nature chose to use. Because when you look closely at the particles in the rulebook, you find something that makes no obvious sense. Nature did not build one set of building blocks. It built 3, and 2 of them fall apart almost the instant they appear. Nature built everything you see out of just a handful of particles, then made 2 extra copies of them for no reason anyone can find. Those spare copies are heavier, they crumble in a flash, and their very existence is one of the oldest unanswered questions in physics. Here is the setup. All the ordinary matter around you, every atom in your body, is built from just a few basic particles. There is the up quark and the down quark, which combine to make protons and neutrons. There is the electron, which orbits around them, and there is a ghostly partner, the electron neutrino. That small kit is enough to build a person, a planet, a star, a galaxy. Scientists call it the first generation. You would think that would be the whole story. It is not. Nature made the same kit again, but heavier. A second generation, with beefed up copies of each particle. The electron's heavier twin is the muon, the same wobbling particle from earlier, and then nature did it a third time, making a third generation, heavier still, topped by the massive top quark. 3 complete sets, 3 generations of matter stacked in order of weight. The strange part is that the 2 heavier sets are useless for building anything permanent. The moment they appear, they fall apart, decaying down into the light-stable first generation in tiny fractions of a second. You cannot make a lasting atom out of them. They flash into being and vanish. So the universe runs entirely on the first generation. The other 2 contribute nothing to the everyday world. They are like spare copies of a tool that shatter the instant you pick them up. Which raises the obvious question. Why are they here at all? Why did nature print 3 sets when one does all the work? When the Mun, the first hint of a second generation, was discovered decades ago, a famous physicist reacted with a single baffled line. Who ordered that? Nobody had asked for a heavier electron, nobody needed one, yet there it was, and then 2 more layers of unnecessary particles turned up behind it. The rulebook happily lists all 3 generations. It describes each one in perfect detail, but it does not explain why there are 3, not 2, not 4, not 7. 3 exactly, and the book is silent on the reason. This is one of the deepest structural mysteries in all of physics, and it has stood unanswered for generations of scientists. Some suspect the number 3 is a clue to a hidden layer of nature, a deeper pattern we have not cracked. Some wonder if there could be even more generations too heavy for our machines to make. So far, careful measurements point firmly to 3, and only 3. But the why remains locked away, and the puzzle of the 3 generations is only the beginning of what the rulebook cannot justify. Because when you open the book and look at the numbers it contains, the actual values that make our universe what it is, you find something that should bother anyone. The most successful theory ever written is riddled with numbers it cannot explain. Dozens of them. And every single one had to be measured by hand, pulled from the real world, because the book itself has no idea where they come from. The greatest theory in the history of science comes with a secret embarrassment. It contains at least 19 numbers that it cannot explain, cannot predict, and cannot derive. Every one of them had to be measured out in the real world and typed into the equations by hand. Think about what a truly complete theory would look like. You would feed in a few basic principles, turn the crank, and out would pour every property of the universe. The weight of the electron, the strength of each force, everything predicted from the ground up, with nothing left over. The standard model does not work like that. It is more like a magnificent machine with a row of dials on the front and the dials are blank. The machine runs beautifully once you set them, but it cannot set them itself. Someone has to go outside, measure the real universe, and turn each dial to match. How many dials? At least 19. 19 separate numbers that the book simply accepts as given. The masses of the quarks and the electron and its cousins. The strengths of the forces. The numbers that control how particles mix and change. Once you include the newly discovered weights of the neutrinos, the count climbs even higher, past 24. None of these values comes out of the theory. They are all measured, all handed to the book from the outside. Now here is the part that should give you chills. Many of those dials are set to eerily precise values, and if you nudge them even slightly, the universe would fall apart. Make the strong force a touch weaker, and atomic centers could never hold together, so there would be no atoms heavier than the simplest one. Make it a touch stronger, and the early universe would have burned through its fuel and left no ordinary hydrogen behind, so there would be no water, no stars like our sun. Change the electron's weight, or the balance between the forces, and chemistry as we know it collapses. The narrow settings that allow atoms, stars, planets, and life sit inside a tiny window. Turn the dials at random, and almost every possible universe comes out sterile and empty. Our universe landed inside the life-friendly window on all of them at once. The rulebook does not say why. It offers no reason the dials sit where they do. It just reports the readings and moves on. This drives scientists a little wild, because a theory studded with unexplained numbers feels unfinished. A real answer, many believe, would derive at least some of these values from a deeper principle, shrinking that row of blank dials down towards 0. So far, no one has managed it. The 19 numbers remain stubbornly free, measured but never understood. And among all those mysterious dials, one group stands out as the strangest of all: the particle masses. Because when you line up the weights of the particles from the lightest to the heaviest, you do not find a neat, gentle pattern. You find a spread so wild, so lopsided, that it looks less like a law of nature and more like a random scattering, from the faintest whisper of a neutrino to a single particle that weighs as much as an entire atom of gold. The range is almost beyond belief. Line up the basic particles by weight, and the spread is so absurd it looks like a mistake. On one end sits the neutrino, so light we still cannot weigh it. On the other sits a single particle that tips the scale as much as a whole atom of gold, and nothing in the rulebook explains the gap between them. Let me walk you up the ladder. At the very bottom are the neutrinos, those ghosts that barely weigh anything at all. Above them sits the electron, itself famously lightweight, yet still at least 1,000,000 times heavier than a neutrino. Keep climbing, and you reach heavier quarks and the muon, then heavier ones still, until you arrive at the champion, the top quark. The top quark is a monster. It is a single, point-like elementary particle, one of the smallest things that exists, with no known parts inside it. Yet it weighs about as much as an entire atom of gold, a clump of 79 protons and even more neutrons all bundled together. Imagine one tiny dot weighing as much as a whole heavy atom. That is the top quark. Now stretch the full range in your mind. From the lightest neutrino to the top quark, the weights span a factor of more than 1 trillion. To picture that, imagine the lightest particle were a single feather. On the same scale, the top quark would weigh more than a mountain. That is the spread nature packed into its basic building blocks, from feather to mountain, with everything else scattered unevenly in between. Here is the deep puzzle. We know how particles get their weight. They get it from the Higgs field, that invisible syrup filling space. The more strongly a particle grips the syrup, the heavier it is. That part the rulebook handles. What the book cannot explain is why each particle grips the syrup by such a wildly different amount. Why does the top quark cling to it like a magnet while the neutrino barely brushes it? The strengths of those grips are among the free dials from before, the numbers measured but never understood. Nature set them to a scattered, lopsided pattern and gave no reason. Scientists have stared at these weights for decades, hunting for a hidden order, some secret formula that would explain the spacing. They have found tantalizing hints and near patterns, but nothing solid. The mass ladder still looks, for all the world, like a set of numbers pulled from a hat. The most fundamental particles in existence weigh what they weigh for reasons no one has cracked, and the masses are only half of this strange bookkeeping. Because the particles do more than sit at their assigned weights, they also transform into one another, one type morphing into a different type, following a set of rules that is every bit as mysterious as the masses themselves. When a quark changes from one kind to another, it does so with certain odds, certain probabilities baked into nature. Those odds are written in a chart of numbers, a kind of secret conversion table that the universe obeys without fail. The rulebook copies the chart down faithfully, and, once again, it has absolutely no idea why the numbers in it are what they are. Quarks can change from one type into another, but only by following a secret table of odds that nature never explains. Scientists have measured this table with enormous care. They still cannot say where a single one of its numbers comes from. Here is the phenomenon. Quarks come in 6 types, and they are not fixed forever. Through the weak force, one type of quark can transform into another. A heavier quark can decay into a lighter one, shifting its identity in the process. This is real and constant, happening inside radioactive atoms all around you and inside the sun this very second. The catch is that not every change is equally likely. A quark is very willing to shift into its close neighbour and very reluctant to leap to a distant one. Those willingness levels are fixed numbers, specific probabilities that nature follows every time. Physicists arrange them into a grid, a chart that lists how eagerly each quark turns into each other quark. It is like a conversion table for the subatomic world. That chart works flawlessly. Feed it into the equations and it predicts how particles decay with beautiful accuracy. It has passed test after test. But the values inside it, the actual numbers, are just more of those blank dials the rulebook cannot fill. Nature chose them. wrote them into the fabric of reality, and left no note explaining the choice. And this chart hides something precious inside it. Buried in those numbers is the tiny flaw in the mirror between matter and antimatter, the very imperfection we chased earlier when asking why the universe contains anything at all. The reason matter and antimatter behave a hair differently traces back, in part, to a subtle twist woven into this quark conversion table. Without that twist, the young universe might have wiped itself out completely, leaving nothing behind. So this small grid of unexplained numbers is tied directly to our existence. You might hope that at least the pattern in the chart made sense, that the numbers followed some tidy rule. They do not. The odds are lopsided in a peculiar way, with quarks strongly preferring their nearest neighbours and only rarely making bigger jumps. Why that particular arrangement? The book is silent. It is one more measured mystery sitting quietly at the heart of matter. For a long time, scientists assumed this quirky conversion table was a one-of-a-kind feature, a strange fingerprint belonging only to quarks. Surely they thought the other particles behaved more simply. Surely this messy mixing was a special case. Then they took a hard look at the neutrinos, and their assumption fell apart. Because the neutrinos, it turns out, have a conversion table of their own. Those ghostly shape-shifting particles mix and transform, following their own chart of numbers, just as the quarks do. Nature built the same kind of strange machinery twice, once for the quarks and once for the ghosts. And here comes the twist that nobody saw coming. The neutrino chart does not look like a copy of the quark chart at all. Where the quarks mix shyly, barely leaning toward their neighbours, the neutrinos mix boldly, wildly, swapping identities with a freedom the quarks never show. Two conversion tables, two sets of unexplained numbers, and they could hardly be more different from each other. Nature built the same strange machinery twice, once for quarks and once for neutrinos, and then made the two versions behave in wildly different ways. Quarks change identity shyly. Neutrinos change identity with reckless abandon, and the rulebook cannot explain either one, let alone why they clash. Remember the quark conversion table, the chart of odds that decides how one type of quark turns into another. The quarks are cautious. They strongly favour shifting into their closest neighbour, and only rarely make a big jump across the family. Their mixing is timid, restrained, gentle. The neutrinos play by a completely different mood. We already saw them shapeshift in mid-flight, morphing from one flavour to another as they fly. That shapeshifting has its own chart of numbers, its own conversion table, and when scientists measured it, they found mixing turned all the way up. Neutrinos swap identities freely and dramatically, blending across their whole family with ease. Where the quarks barely lean, the neutrinos swing wide open. Picture two dancers. The first, the quark, mostly stays in place, giving only a small, careful sway toward a partner beside it. The second, the neutrino, spins across the entire floor, changing partners with wild energy. Same dance, same basic rules, utterly different style. And nobody knows why the two move so differently. This is a genuine puzzle, and it cuts to something fundamental about how nature is built. Both charts are made of those free numbers the book cannot derive. But the deeper mystery is the contrast. If both quarks and neutrinos are built from the same underlying rulebook, why does one mix so shyly and the other so boldly? They are following the same basic music, yet the choreography could hardly look more opposite. Something must be shaping these patterns, some hidden principle steering the numbers. The rulebook shows us the result and hides the cause. There is more riding on the neutrino chart than elegance. Just as the quark table held a tiny flaw in the mirror between matter and antimatter, the neutrino table might hold a flaw of its own, possibly a much larger one. Scientists are racing right now to measure it, because if neutrinos break that mirror strongly, they could hold the missing answer to why matter beat antimatter in the young universe. That search is one of the hottest frontiers in physics today, still unfolding, still unsettled. So we have two conversion tables, two sets of mysterious numbers, and a glaring difference between them that cries out for an explanation the book cannot give. The mixing of matter is one more crack, one more place where the rulebook records what happens without understanding why. Now, all of this mixing, both the quarks and the neutrinos, involves that delicate mirror between matter and antimatter. And that mirror leads us to one of the strangest puzzles of all. Because there is a place in physics where the mirror could easily crack, where the math practically begs it to crack, and yet it stubbornly refuses to. One of nature's forces has every opportunity to treat matter and antimatter differently. The rulebook allows it. Nothing forbids it. And when scientists check, they find the force behaving with perfect, flawless fairness, balanced to a degree so extreme it looks almost deliberate. One of nature's forces is suspiciously, impossibly fair, and its perfect fairness may be hiding a whole new particle. The strong force, the one that glues the centers of atoms together, has every chance to treat matter and antimatter differently. It simply does not. And the exactness of its balance is a mystery that has puzzled physicists for half a century. Here is the situation. The math that describes the strong force contains a knob. This knob controls how much the strong force would tilt the scales between matter and antimatter, breaking that mirror we keep returning to. The knob could be set to any value. There is no rule in the book forcing it to any particular spot. It could be turned way up, making the strong force wildly unfair. It could sit anywhere across a huge range. If the knob were turned up even a little, it would have a visible effect. It would make the neutron, one of the particles inside every atom, behave like a tiny lopsided magnet with a slight electric tilt. Scientists have hunted for that tilt with extraordinary care, building experiments sensitive enough to detect the faintest hint of it. They have found nothing. As far as anyone can measure, the tilt is zero. The knob, which could point anywhere, is sitting almost exactly at zero, balanced to better than 1 part in 10 billion. Imagine a dial that could land on any number across a vast range and finding it parked precisely on zero, with more than 10 zeros of accuracy behind it. That is what nature appears to have done, for no reason the book can offer. Scientists call this the strong force fairness problem, and it drives them a little crazy. A knob set to exactly zero, when it could have been anything, cries out for an explanation. Random chance seems absurd. Something, they suspect, must be forcing that knob to zero, holding it there, some mechanism the rulebook does not include. And that suspicion led to one of the boldest ideas in modern physics. To explain the perfect fairness, some scientists proposed a brand new ingredient in nature. They imagined an unseen field spread through all of space that would automatically relax the knob down to zero, the way a ball rolls to the bottom of a bowl. If such a field exists, it would settle the strong force into perfect fairness naturally, with no fine-tuning required. But a new field comes with a price. It cannot hide silently. If this field is real, it must ripple, and its ripples would be a brand new particle, one absent from the entire rulebook, a particle invented on paper to fix a puzzle, waiting to be found in the real world. Scientists gave this hypothetical particle a name. It would be almost unimaginably light, far lighter than anything we have confirmed, and it would barely interact with ordinary matter, making it fiendishly hard to detect. A ghost invented to explain the fairness of a force. And here is the twist that turns a niche puzzle into a cosmic one. If this ghostly particle exists, and if it fills space in vast numbers, it might be the very thing we have been hunting all along. It might be the dark matter, the invisible mass that outweighs every star. A particle invented on paper to fix one obscure puzzle might turn out to be the invisible glue holding every galaxy together. Scientists call it the axion, and the hunt for it has become one of the great treasure hunts of modern physics. Remember where it came from. To explain why the strong force is so perfectly fair between matter and antimatter, physicists dreamed up an unseen field that relaxes nature's knob to zero. The ripples in that field would be a new particle, extremely light and extremely shy. That particle is the axion. It began its life as a clever fix for a narrow problem. Then scientists realized something wonderful. If axions are real, the young universe would have produced them in staggering numbers. Countless axions drifting through space, so light and so shy that they neither shine nor block light, gripping the cosmos only through gravity. That description should sound familiar. It is almost a perfect match for dark matter, the invisible mass we have been chasing this whole journey. So the axion wears two hats. It could solve the strong force fairness problem, and it could be the dark matter all at once. One idea, two of the biggest mysteries in physics potentially answered together. For many scientists, that double payoff makes the axion the most exciting suspect on the board. The trouble, as always, is catching one. An axion barely touches ordinary matter, which makes it a nightmare to detect. But scientists found a possible chink in its armour. In the presence of a very strong magnetic field, an axion might, on rare occasion, transform into a faint flicker of light. That gives hunters a target. So they built extraordinary machines. Picture a powerful magnet wrapped around an exquisitely sensitive receiver, cooled to near the coldest temperature possible, tuned like a radio dial. The idea is to sweep across possible axion frequencies, listening for the tiny whisper of light that a passing axion would make as it converts inside the magnet. It is like trying to tune into a single, impossibly faint radio station hidden somewhere across an enormous band. The searches are underway right now in labs around the world, each one scanning new territory, each one pushing sensitivity higher. So far, no confirmed axion has turned up. But unlike some dead ends, this hunt is very much alive. Every year the detectors improve, and every year they rule out more hiding places and creep closer to where the axion, if it exists, should be lurking. The axion remains a theory, an elegant guess, unproven. It might be real and waiting just beyond our current reach. It might not exist at all, and the strong force's perfect fairness might have some entirely different cause. Nobody yet knows. What makes the axion special is how much it would explain if it were found, tying a subtle force puzzle to the invisible skeleton of the universe. The axion is a new particle invented to patch a hole in the book, and it is far from the only one. Scientists have proposed other hidden particles too, ghosts beyond the known ghosts, to explain other stubborn puzzles. One of them may be lurking among the neutrinos themselves, a fourth kind of neutrino so shy that it ignores every force but gravity, a ghost even quieter than the ghosts we already know. There may be a particle so shy that it makes the neutrino look sociable. It would ignore almost every force in nature, drifting through the universe touched only by gravity, a ghost hiding among ghosts. Scientists call it the sterile neutrino, and its existence would crack the rulebook open in a fascinating way. Start with the neutrinos we know. They already barely interact, slipping through planets untouched. But they do feel one force besides gravity, the weak force, and that faint touch is the only reason we can detect them at all. Every neutrino experiment relies on catching that rare, gentle, weak force nudge. Now imagine a neutrino that does not even feel the weak force, a neutrino that responds to gravity alone and nothing else. It would be almost perfectly invisible, unable to be caught by any of our usual tricks, since those tricks all depend on the weak force. Scientists call such a particle sterile, because it stays aloof from the forces that let us see ordinary neutrinos. It would be the most antisocial particle ever proposed. Why think it exists at all? Because a handful of experiments over the years have coughed up strange results, small anomalies that do not quite fit the picture of just 3 neutrino types. In certain setups, neutrinos seem to appear or vanish at rates the standard 3 neutrino story struggled to explain. One tempting way to make sense of those oddities is to add a fourth, hidden, sterile neutrino quietly influencing the others. If it were real, the payoff could be huge. A sterile neutrino might help explain those puzzling experiments. It might even be another candidate for dark matter, joining the axion on the list of invisible suspects, and it would prove that the rulebook's neat count of particles is incomplete, that there are whole players hiding just out of view. So scientists went looking, building dedicated experiments to hunt the fourth ghost. They fired neutrinos across carefully measured distances and watched for the telltale fingerprints a sterile neutrino would leave behind. The results have been a tangle. Some experiments hinted at something. Others, more sensitive, looked in the same place and found the simplest version of the idea wanting, squeezing the sterile neutrino into ever tighter corners. As things stand, the sterile neutrino is unconfirmed and hotly debated. It has not been ruled out entirely, and it has not been proven. It sits in that uncomfortable grey zone where a few clues point one way, sharper tests point another, and the community argues over what it all means. The fourth ghost may be real, or the anomalies may fade as our measurements improve. This one is still genuinely open. What the sterile neutrino shows is a pattern in how physicists think. When the rulebook falls short, they propose new particles to fill the gaps, a ghost to fix the strong force, a ghost to fix the neutrino puzzles, one at a time, cautiously. But some scientists took a far bolder swing. Instead of adding one hidden particle here and another there, they proposed doubling the entire particle world in a single stroke. They imagined that every particle we know has a secret heavier twin, a whole mirror family waiting to be discovered. It was one of the most beautiful ideas physics ever produced, and the biggest machine humanity has ever built went looking for it. Imagine that every particle in the universe has a secret twin, a heavier partner nobody has ever seen. That single idea, called supersymmetry, was so elegant that thousands of physicists believed it had to be true. Then the most powerful machine ever built went hunting for those twins and came back empty-handed. Here is the beautiful idea. The particle world splits into two broad types, the ones that make up matter and the ones that carry forces. Supersymmetry proposes that each particle in one group has a hidden partner in the other. Every matter particle would have a force-type twin, and every force particle would have a matter-type twin. A whole shadow family, doubling the cast of nature. Why would anyone believe something so extravagant? Because it would fix things, several things at once with startling grace. Remember the hierarchy problem, the mystery of why the Higgs is so impossibly light, despite all those tugs trying to make it heavy. Supersymmetry solves it almost for free. The hidden twins would push on the Higgs in the opposite direction, cancelling the dangerous tugs and holding its weight down naturally, with no fine balancing act required. The gifts do not stop there. The lightest of these twin particles would be heavy, stable, and nearly invisible, interacting only weakly with ordinary matter. In other words, it would be a picture-perfect candidate for dark matter, and supersymmetry would also help the three forces of the rulebook line up neatly at high energies, a clue we will reach soon. One idea, and suddenly, three of the biggest puzzles in physics start clicking into place. It was, and is, breathtakingly tidy. For decades, supersymmetry was the great hope, the favourite theory of the future. Physicists were so confident that when they built the Large Hadron Collider, the giant ring straddling the border of France and Switzerland, many expected the twin particles to appear almost immediately. The machine smashes protons together at nearly the speed of light, and if the twins existed within reach, the debris of those collisions should reveal them. The collisions came by the trillions. Scientists sifted through the wreckage with painstaking care, looking for any sign of the predicted partners, and the partners did not show. Not in the first run, not in the second, not after years of searching at higher and higher energies. Every hiding place the machine could probe came up empty. That absence stung. The simplest, most elegant versions of supersymmetry, the ones that solve the hierarchy problem most beautifully, are exactly the ones the Collider should have found first. Their no-show has pushed those clean versions to the brink. The twins, if they exist at all, must be heavier or stranger than the tidy theory predicted, hiding beyond the reach of even our mightiest machine. So supersymmetry sits in limbo. It remains a gorgeous idea that would explain so much. It has not been ruled out completely since nature could have placed the twins just past where we can currently look. But its silence has humbled a generation of physicists who were sure it would appear. Beauty, it turns out, is no guarantee of truth. Supersymmetry was meant to be a stepping stone toward an even grander dream, a single theory that unites the forces of nature into one, and that grand dream makes a startling prediction, one that would mean even the most solid matter in your body is quietly living on borrowed time. The protons inside you may be slowly dying, not in your lifetime, not in 1 trillion lifetimes, but eventually, according to some of the boldest theories in physics. If they are right, then matter itself is temporary, and even the atoms in your bones are on a countdown. Here is where this idea comes from. The rulebook has 3 forces, and they feel like separate things, each with its own strength and its own rules. But many physicists suspect that at incredibly high energies, like those in the first instant after the Big Bang, those 3 forces merge into a single unified force. Theories that try to describe this merger are called grand unified theories, and they are among the most ambitious ideas ever proposed. These grand theories make a shocking prediction. If the forces were once one, then the sharp walls between different particles blur, and that means a proton, one of the rock-solid particles at the heart of every atom, would no longer be perfectly stable. Once in a great while, a proton could fall apart, decaying into lighter particles and radiation. The most permanent-seeming matter in the universe would have an expiration date. We normally think of protons as eternal. They have sat inside atoms since the early universe, unchanged for billions of years. The idea that they might crumble strikes at the foundation of everything solid. If protons decay, then given enough time, all ordinary matter would eventually dissolve. Stars, planets, people, all of it slowly evaporating into a thin haze of light and lighter particles across unimaginable stretches of time. So scientists went looking. If protons decay, you could catch one in the act, provided you watched enough of them for long enough. So they built enormous underground tanks filled with ultra-pure water, the same kind of detector that caught neutrinos shape-shifting. A single large tank holds a staggering number of protons, far more than 1 trillion of them, all sitting there, all being watched around the clock for the faint flash a dying proton would make. They have watched for years, and so far, not a single proton has been seen to die. That silence is itself powerful. It tells us that if protons decay at all, they must live for an almost incomprehensible span of time. Scientists have pushed the proton's minimum lifetime out past a number with more than 30 zeros in it, in years. Compare that with the age of the whole universe, which has a mere 10 zeros. A proton, if it dies at all, outlives the entire cosmos by a factor beyond imagining. That leaves us with 2 possibilities, and both are interesting. Maybe protons truly are immortal, and the grand unified theories are simply wrong, at least in their simplest forms. Or maybe protons do die, but so rarely that we need even bigger detectors, watching even longer, to ever catch one. The hunt continues, with new and larger tanks being built to push the search further. Grand unified theories predict a dying proton, and we have never seen one. But that is not the only strange thing these theories conjure up. They also predict a bizarre object that should be scattered across the universe, an object so odd that finding even one would rewrite physics. It is a magnet with only a single pole, and despite decades of searching, not one has ever been found. Every magnet in the world has 2 poles, a north and a south, and no one has ever found one with only a single pole. Yet the deepest theories in physics insist that such an object should exist, scattered somewhere across the universe. Its stubborn absence is a mystery all its own. Try a simple experiment in your mind. Take a bar magnet. It has a north pole at one end and a south pole at the other. Now snap it in half, hoping to separate the two. You do not get a lone north and a lone south. Instead, each broken piece instantly grows its own new pair, a fresh north and south. Snap those again, and it happens once more. No matter how many times you cut, you always get complete pairs. A single, isolated pole seems impossible, but physics predicts one should exist. A magnetic monopole would be a particle carrying just one pole, a pure north or a pure south, all by itself. The great physicist who first explored the idea showed that a single monopole, anywhere in the universe, would elegantly explain another deep mystery, namely, why electric charge always comes in tidy, exact packets. And later, the grand unified theories we just met went further, insisting that the young universe should have produced monopoles in huge numbers. That last part created a genuine crisis. If the early universe made monopoles as freely as the theories suggested, the cosmos should be swarming with them today. They should be common, showing up in our detectors, littering the galaxy. Instead, we see none. Not one confirmed monopole, ever, despite decades of dedicated searching. That glaring absence actually helped spark one of the biggest ideas in cosmology. To explain where all the monopoles went, scientists proposed that the infant universe underwent a sudden, colossal growth spurt, ballooning in size almost instantly. Such a burst would have spread any monopoles so thinly that we would be lucky to find even one in the entire observable universe. This growth spurt idea has since become a cornerstone of how we understand the early cosmos, and the missing monopoles were part of its inspiration. Scientists have not given up the hunt. They have searched for monopoles in cosmic rays raining from space, in ancient rock, in the debris of particle collisions. Once, decades ago, A single detector recorded one tantalizing blip that looked exactly like a monopole passing through on a winter night. It caused a stir, but it never happened again, and a lone, unrepeatable event cannot count as a discovery. The blip remains a haunting maybe, nothing more. So the magnetic monopole sits in a strange place. Our best theories say it should exist, some even say it must. Its presence would explain beautiful things about the structure of nature, and yet, after all this searching, the universe has refused to hand us even one. It is a prediction hanging in mid-air, waiting for evidence that stubbornly never comes. The monopole and the dying proton both flow from the same grand dream, the idea that the forces of nature were once united as one. That dream rests on a single, testable hope, that if you could crank the energy high enough, the separate forces of the rulebook would converge and merge into a single mighty force. So scientists checked whether the forces really do line up, and what they found was almost, but frustratingly not quite, perfect. The three forces in the rulebook may have been a single force once, at the dawn of time, and we can almost prove it. Almost. When scientists trace the forces back toward their origin, the three lines rush together and very nearly meet at a single point. Then they miss by a hair, and that near miss is one of the most tantalizing clues in all of physics. Here is the key fact that makes this possible. The strengths of the forces are not truly fixed. They change depending on the energy of the collision you use to probe them. At everyday energies, the three forces of the rulebook, the strong, the weak, and electromagnetism, have very different strengths. But crank the energy higher and higher, and those strengths begin to drift, some growing, some shrinking. Scientists can calculate exactly how each force changes with energy, then extend those lines far, far beyond any energy we can reach in a lab, all the way up toward the conditions of the newborn universe. And when they do, something remarkable happens. The three lines, starting so far apart, sweep toward each other and nearly converge on a single spot. Three separate forces, apparently trying to become one. This is the beating heart of the grand unified dream. If the three lines truly met, it would strongly suggest that all three forces were once a single, unified force in the blazing heat of the early universe, later splitting apart as the cosmos cooled, like a single language slowly branching into three separate tongues. It would be one of the most profound discoveries imaginable. But in the plain rulebook, the lines do not quite meet. They come stunningly close, close enough to make your heart race, and then they cross at slightly different points, missing the perfect single meeting by a small margin. So near, and yet not there. It is like three roads racing toward the same intersection and arriving just barely out of step, passing through almost the same point but not exactly. That near miss could mean two very different things. Maybe the forces were never truly one, and the close approach is just a coincidence, a tease with no deeper meaning. Or maybe the miss is telling us that the rulebook is incomplete, that some missing ingredient would nudge the three lines into perfect alignment. And here is where an earlier idea comes roaring back. Remember supersymmetry, the theory of hidden twin particles that the Great Collider has so far failed to find. When scientists add those twin particles into the calculation, something beautiful happens. The three lines shift, and they meet, not almost, exactly. The near miss becomes a perfect bullseye. That is one of the reasons physicists loved supersymmetry so much. It took the tantalizing near miss of the forces and turned it into a clean, unified point. The trouble, of course, is that the twin particles have not shown up, so the perfect meeting depends on a theory still waiting for proof. For now, the three forces remain almost, but not quite, one. The clue dangles in front of us, gorgeous and unresolved, hinting at a hidden unity we cannot yet confirm. While physicists chase these grand ideas about the beginning of everything, a fresh crack has been spreading at the opposite end of the cosmos, at the largest scales of all, and this one is happening right now in real time as scientists watch. Right now, in real time, scientists are watching a crack spread through one of their most trusted ideas about the universe. The culprit is dark energy, the mysterious force pushing space apart. And the newest maps of the cosmos hint that this force may be weakening, something almost no one expected. Recall what dark energy does. It is the invisible pressure driving the universe to expand faster and faster, and it makes up the largest share of everything, around 2/3 of the whole cosmos. For a long time, scientists assumed dark energy was a constant, an unchanging feature woven into the fabric of empty space, the same strength yesterday, today, and forever. That assumption sat at the centre of our best picture of the universe. To test it, scientists built an extraordinary instrument, a telescope survey designed to map the cosmos in 3 dimensions. It uses thousands of tiny robotic eyes to capture the light of millions upon millions of galaxies and quasars, charting where they sit across billions of light years. The result is the largest 3-dimensional map of the universe ever made, a vast atlas of cosmic history stretching back through time. By reading that map, scientists can measure how the expansion of the universe has changed over billions of years, and from that, how dark energy has behaved across cosmic time. If dark energy were truly constant, the map should show it holding perfectly steady. That is what everyone expected to see. That is not quite what the map showed. When scientists combine this giant cosmic atlas with other measurements, the light from the young universe and the glow of distant exploding stars, they saw hints of something strange. The data leaned toward a dark energy that was stronger in the past and has been weakening as the universe ages. A dark energy that changes. A dark energy that fades. If that turns out to be real, it would be an earthquake in physics. A changing dark energy would break the simple, constant picture we have leaned on for decades. It would mean the dominant ingredient of the universe is something dynamic and evolving, governed by rules we have not written down. And it would reshape our guesses about how the cosmos will end, whether it drifts apart gently or meets some stranger fate. Now for the honest caution, because this is science in the making. The hints are strong, but they have not yet reached the towering level of certainty that physicists demand before they will call something a discovery. The signal sits in a tense middle zone, exciting but unconfirmed. Some scientists are thrilled, convinced we are glimpsing new physics at last. Others urge patience, warning that subtle errors in combining different measurements could be fooling us. The debate is live and unsettled. What makes this moment special is that it is unfolding as we speak. Fresh data is pouring in. Bigger cosmic maps are being drawn. Within a few years, the hints will either harden into a stunning discovery or melt away as the measurements sharpen. We are watching in real time to see whether the rulebook of the universe is about to gain one of its most dramatic new chapters. And that is the thread tying this entire journey together. Every crack we have walked through, from the tiniest wobbling particle to the largest structures in the cosmos, points to the same electrifying truth. Our finest theory of reality is not the end of the story. It is only the beginning. Everything you are made of runs on rules that scientists have not finished writing. That is the real ending of this journey, and it might be the most thrilling part of all. The Standard Model, our greatest scientific achievement, is a masterpiece filled with holes, and every hole is a door. Look back at how far we have come. We started with a rulebook so accurate it predicts nature to more decimal places than we can picture. Then we watched it fall silent, again and again, on the biggest questions there are. It cannot explain gravity, the force holding you in your seat. It has no page for dark matter, which outweighs every star 5 times over. It cannot name dark energy, the thing that fills most of the cosmos. It cannot say why matter exists at all, why you exist, when the universe should have annihilated itself into empty light, and the holes go deeper still. The book cannot explain why particles weigh what they weigh, spanning from a ghostly neutrino to a single particle as heavy as an atom of gold. It cannot say why nature made 3 copies of everything. It cannot explain 19 of its own numbers, each one tuned so finely that a small change would erase all atoms, all stars, all life. It leaves the Higgs impossibly light, the vacuum balanced on a knife's edge, and the forces almost, but not quite united. Here is the beautiful part. Every single one of those gaps is an invitation. Each blank space is a place where a discovery is waiting, where the next great leap in human understanding is hiding, ready for someone to find it. And people are looking right now with everything they have. Scientists are dreaming up colliders far larger than any built before. Machines with rings stretching more than 50 miles around, powerful enough to hunt for the hidden twins and the missing particles that our current tools cannot reach. They are burying ever more sensitive detectors deep underground, waiting for a single dark particle, a lone axion, a dying proton. They are building bigger cosmic maps to track where the dark energy is truly fading. They are racing to measure whether the ghostly neutrinos hold the secret of why anything is here at all. Some of the people who will crack these mysteries are alive today. Some of them might be your age. The person who finally explains dark matter, or catches the first proton dying, or proves what came before the Big Bang, may be sitting in a classroom this very moment, staring out a window, wondering how the universe works. That is the feeling I want to leave you with. We live in a rare and electric moment. We have a rulebook good enough to reveal exactly where it breaks, and honest enough to admit how much it does not know. The map has edges, and just past those edges lies unexplored country waiting. The atoms in your body, the light in the sky, the space between the stars, all of it obeys laws we have only half discovered. The rest of those laws are still out there, hidden in the dark, waiting for a curious mind to bring them into the light. The universe kept its rulebook incomplete, and that means the greatest chapters have not been written yet.